All right, I want to talk about energy diagrams. So what I have here is potential energy as a function of x versus x. And just want to make sure I have my pen on. I want to talk about equilibrium. And if you remember what equilibrium is where F, right, where the net force is 0. Okay, well, do we know any relationship between F and U? I hope so. And that is the relationship. So if F is negative du dx and we have a graph of u versus x, what is that on the graph? And hopefully you realize it is slope, okay? So if it's equilibrium, then that means the slope has to be 0. So where on this graph, let's change colors, where on this graph is the slope 0? And there the slope is 0, and there the slope is 0. So those are both equilibrium points, okay? And then like if this was actually also maybe potentially, okay, just, depending on how I drew it. Okay, so these are equilibrium, but these are different kinds of equilibrium. And I will, in the next slide, go back to black, okay? There's something called a stable equilibrium and an unstable equilibrium. And I'm sure that you know this just from your own life, right? If I have a bowl and I have a little marble right here at the bottom of the bowl, it's very happy there. It is in equilibrium, okay? What if I give it like a tiny nudge that way, okay? So now, let's draw it in a different color. Okay, so now I want you to imagine that this ball is here. What does it feel, right? It feels a force that way, right? And then, so it'll go down that way, and then say it's up here, and it feels a force that way. So what does that force that it feels is, wait for it, the negative slope of the curve, right? This is really, this little U-shaped thing is really a curve of U, right? It's the U versus X, right? And it feels, it feels a force in the opposite direction of that slope. So what I'm meaning to say here is this is a positive slope, which gives you a force in the negative direction. Here, that's a negative slope, and that means it's a force in the positive direction. Sorry, I was running out of room there. Boom, feels a force down. So this looks like, right, a restoring force, because it wants to go back. It wants to go back to equilibrium. Okay, that is what stable equilibrium is. It's a situation where if you give a little bit of a perturbation away from equilibrium, it will come back. Okay, that's what stable is. All right, for unstable equilibrium, you want to think about something on the top of a hill. Right here, it is at equilibrium point, right? It is not moving, force is 0, boom. But if I give it a tiny little nudge, then what happens? So it's gonna be right here. What is that slope? That is a negative slope, which means it's going to feel a positive force. Positive is in that direction. Okay, and if you come down here, if you nudged it the other way, this slope is a positive slope, and so it is going to feel a force in the negative direction. So when you're in this situation, so an example, right? So this is called unstable equilibrium. Okay, so right, the force pushes away from the center, right? And here the force pushes toward the center. And so just to give you real life thinking, the stable equilibrium, a marble in a bowl is perfect. Unstable ball on the top of a hill. Or you can also think about if you tried to stand like a dry erase marker straight up, it's very happy right there, unless you give it a little bit of a shove, and then it'll go, it'll fall over, right? So, how do you relate this some calculus? Because I know you love your calculus. All right, so talk to me about these. All right, how do we know that we have that, right? So the f is negative du dx equals 0. So the first derivative equals 0. But what is the second derivative here? And actually I will erase that equal sign, and I will place it with that, right? Concave up. And so this guy is, the second derivative is less than 0, and it's concave down, right? All right, so again, that was unstable, and that was stable. All right. Okay, so let's talk about some other things that we can do with energy diagrams. So let's say I have a boulder at the top of the hill, and it rolls down, and then there's another hill on the other side. Okay, so let's draw the potential energy curve. Let's start here, where it's like at the top of the hill. As it moves, it's going to go down, and then here it is at the bottom of the hill. And that was an amazing curve that I just drew. Yes, you're welcome. Okay, so then it starts rolling back up the hill. So the question is, how far up the hill does it go? We're going to hold off on that for a second, okay? Because I want to also talk about kinetic energy. Let's pick a different color for that. At the top, the kinetic energy is 0, okay? So blue is kinetic energy, red is potential. Okay, so what is happening here? At the top, it has no kinetic and it's all potential. So if I want to talk about the total energy, so I'll pick green, total mechanical energy, okay, that's kinetic plus potential, right? So if I have no kinetic and all potential, then this is my total energy. Well, what do we know about the total energy? The total energy is going to stay the same, okay? So this is total energy. So as this thing moves, let's try to figure out what our kinetic energy looks like. I need to go back to blue. So it is true that the whole entire time that the kinetic plus the potential has to equal this total. So the potential goes down a little bit here, so the kinetic goes up a little bit here, and at every point, and I'm not sure if my curve, like my slope is that's a little bit funky near the end. Okay, let's just boom. All right, that's a little better. But at every point, my kinetic plus potential equals my total, okay? So if I ever want to know, and this is a fun, awesome, important trick, okay? If I want to know the kinetic energy at a certain point, okay? So now just to not confuse you, I'll go back to black, okay? If I wanted to say, what is, right, x, the kinetic energy at this x, let's say 1, okay? I know the potential energy, right? That potential energy is this value. I know the total energy is this value. So the distance between the potential energy line and the total energy line is the leftover energy, which is in the form of kinetic energy. That's a really common problem that you'll see, okay? But what's important about the total energy is that this was the amount of energy that it had at the beginning, and it can't ever get more, right? Because there's no external work on the system, all right? And so this thing is never going to go back up higher than it started over here, okay? Okay, I want to point out where sometimes people get confused with these energy diagrams, okay? This is energy versus a position. This is not energy versus time. I think we're very used to thinking about when we're looking, from left to right on a graph, we're sort of in our heads going sort of chronologically through time, right? So I want to show you something where that really is not happening, so that we can try to wrap our brains in a different way around this stuff. So I want to look at an object in vertical free fall, okay? The energy of this object, right? Do we know the potential energy function? I hope so. Potential energy function for the height above ground, it's going to be like this, right? Where U equals mgy. Okay, remember, this is just a function, right? Energy versus height, right? So that's y. And so that's our potential energy function. All right. Okay, so if we wanted to talk about just the total energy that this thing has, we can think about sort of where does it start, right? There's some kind of y maximum that it has, right? So if I indicate that here, and of course that was annoying where I put the label for the axis. If this was my y max, right, and then this, and I'll try to use the same colors as I did before, that is my total energy, right, is where this thing is at the highest point, okay? So if I wanted to look at sort of a certain height, I don't know, let's call that y sub a, just a point. So y sub a. So let's do the right color coding thing here. The value of the potential energy, U, right, at point A is given by that function, right? And so the question is, what is its kinetic energy? Its kinetic energy has to be the difference between the total energy and the potential energy there, okay? So what you can see is that here, right, at y not equals 0, right, that's the ground, or the lowest point of which we're looking, then it's the biggest that it can get, right? Because the total energy has to be the kinetic plus the potential, and if this is 0 potential, then you've got max kinetic energy, okay? The other thing to notice is that this part of the graph is not physically allowable. The potential energy can never be more than the total energy, okay? Okay, and finally, I want to talk about a situation like this. This is like a box between two springs, and it's going back and forth. In all these situations, the actual value, the actual dissipative forces are non-existent. These are all with conservative things. Okay, so hopefully you remember that the potential energy for a spring is 1/2 kx squared. Okay, and this position right here is where, right, is the equilibrium point for the springs. Okay, so this function u of x is 1/2 kx squared. Okay, so what is actually happening? This axis, the x-axis, is displacement from equilibrium, right? So we have positive displacement and we have negative displacement, okay? And this thing is going to oscillate between sort of an x max and a negative x max. We're going to get more into this kind of stuff when we go back to do simple harmonic motion. But for right now, we're just mentioning it for energy purposes, okay? So the question is, where does this thing turn around? Well, it turns around at x max, right? At x max, it has no kinetic energy. So this is the total energy. So that's the whole idea about what a turning point is, okay? Turning point is where the kinetic energy is 0, right? Think about any turning point that you think of. Turning point means kinetic energy is 0. So I'm going to write that this is a turning point. They very often ask about turning points. This is also a turning point, of course. So that's where the kinetic energy is 0. And if we took a random position right here, then our potential energy is that. And so our kinetic energy will be that, right? Because they have to add up. And again, when you're thinking about, this is still the same kind of idea when you're thinking of the slope is the force. So if you take any point on any of these, on this potential energy function, just get black, right? Here you go. It's a positive slope, so the force is going to be that way, all right? Negative. These energy diagrams are super duper rich. There's a lot of information in it, and I would really encourage you to take some time and really just try to get all the information out of it that you can. All right, that's a good place to stop.